嗯嗯嗯，Hello，Hello，Hello，嗯嗯嗯。 Hi, Professor. Morning.
Let's see.
Hi, Professor Wang.
Hello.
Hey, hello.
Morning.
Morning.
Hi, Rich. Hi.
Hi.
Okay, good. So it works. Good morning.
Morning. Morning, Professor.
Zoom actually works this morning. That's good. I find that for all the billions of hours of Zoom calls that people have had over the last year, they still fail sometimes on getting the audio set up right. You would not think it would be that hard.
Yeah, sometimes it's tricky. The Zoom actually allows you to choose the source and
Sure.
the device to play the audio.
I know, but I've had calls where I can choose the source, the test speaker works, the test microphone works, but they can't actually hear it on the other side. I've had that worse with Skype, which I guess is now an orphan technology that Microsoft uses Teams. And it's not always working. Oh, good. New measurements.
It's interesting.
That's interesting. Antenna is a mirror image in the diagram. Must have flipped the picture over.
Yeah.
I was in a talk once where somebody was talking about vision and how your eyes can trick you. And he put a slide on the screen that looked like it was upside down, a view graph on the projector. Looked like it was upside down. And the person that was showing it kept flipping it over, trying to get it right side up. And it wouldn't go. It flipped it this way and that way. What he had done is he flipped each letter individually. So it looks like it's backwards, but it's going backwards in the other direction. There's no operation you can do on the whole view graph that makes it correct.
So there's some AI technology behind that?
No, it's just, you don't need artificial intelligence when you have natural stupidity. I guess you still have that in some of these video calls because you can get a reflected or a mirrored or a direct image.
Yeah,
camera.
I think Zoom has it.
Right.
You can choose mirror the video, so
right,
the left and right will be switched.
Good position, vertically different body positions. Just out of curiosity, did you talk about moving the tags to different places and having it affect the signal? Did you actually try moving the tags like a centimeter at a time and see what it looks like to make a map?
Yeah, just a 3 distance, 100 centimeters and 200 centimeters and 300 centimeters.
No, I meant the blue tags on the chest.
Oh, chest.
Right.
A chest.
Put a little mark on it, with tape, and just move it a centimeter at a time and see what the map looks like.
Okay, I have it such as this.
Yeah. Okay.
Yeah, this is a vertical tag, and also in the previous, I think in the here. So here is horizontal tag. Yes.
Right. Right.
Yeah.
But if you're trying to measure the sensitivity, You can take just one tag and just move it, make measurements by moving it a centimeter at a time, make a measurement and plot it up to see how actually, if you can see how sensitive it is. Saying that in 2 positions it's sensitive implies that there's some kind of underlying function that you can plot out and learn something about how sensitive it actually is. And the same thing going out, and going up and down and left and right, you can actually make a map of the sensitivity that way pretty easily.
Okay.
And would give you a visual perspective on what's going on.
Okay.
And I mean, I don't know, these measurements are pretty quick, right?
Yeah.
Right. So I can imagine making an XY map on your chest of one tag and do see also different layers of foam under it, move it away from your skin. And then you would have a real idea of what's going on and how sensitive it is.
Okay. So
just a thought.
But Professor, we have the questions. So we found that the RFID signal are sensitive to the environment and maybe to the different human. Yeah,
absolutely.
So, that's right. That's right. It should be.
Okay.
Okay.
Okay. So I go back to the first.
You want to know how it's sensitive. Yeah.
Okay, I go back to the first slide.
Yeah. Let's get started.
Okay, so
you
now
can continue. I think you continue to certain points already. Sorry that
no, we haven't started yet.
Oh, okay. Because I need to update my Zoom. Somehow it asked me to update, so it takes.
Yeah, mine did too.
Yeah, I need to update it too. Okay, now I'm reporting my work in progress. So for these 2 weeks, we conducted multiple experiments to explore the impact of the various factors such as tag location, direction, distance on the breathing sensing. So for this week, we conducted 5 sets of experiments. The first one is attached 1 tag and 2 tags on the water bottle at different positions to explore the impact of the background noise. Second one is that we attached 1 tag horizontally on the good position that we found by the previous experiment at a different distance to explore the impact of distance. The third one is that we attached 1 tag vertically on the different body positions. Fourth one is we attached 1 tag with different directions on the good positions. Last one is we attached 2 tags with different arrangement to explore the impact of the tag arrangements. And below 2 figures shows the experiment setup. And the next page I shows the details for each experiment setup. The first one is experiment 1 setup. So in this experiment, we have 5 scenarios. The first one, we direct attached the tag on the bottle with water. But in this scenario, we cannot get any signals. So we let the bottle wear the clothes in the 2 to 5 scenarios and attach the tag in different positions. In the 4 and 5 scenarios, we use the tag arrays and with different distance between the tags. This is the first experiment. The second experiment setup is that we have already found a good position near is the boundary of the chest and the abdominal. So in here, I use the 3 different distance between the antenna and the subject. We use the 100, 200, and 300 centimeters to conduct the experiment. Also, we use the respiration monitor bite to collect the ground truth.
So Bing, do you want to, like, for every experiment, after you talk about experimental setup, you show us the results instead of going the details of all the detailed experiments? Then go, so that we can come, corresponding to each one. So let's go to the results first.
So this slide 8 shows the summary of the experiment.
So you don't have the one corresponding to experiment 1?
Yeah, we have that in here, 9. So the summary for experiment 1 is that because the scenario 1, we cannot get any signals. So for another 4 scenarios,
Why
we
for
can-
scenario 1 you cannot get any signals?
yeah, we conduct experiments. We attach the signals. We attach the tags directly on the bottles and directly on the skin, so we cannot get any signals. So we think
That's
maybe
strange, right? You put it on the water bottle or put it on your clothes.
yeah, put on the skin. We cannot get.
You didn't put it on the skin, right? It's put on the water bottle. Experiment 1, there's no person there, only water bottle. There's no
Water bottle.
skin.
No skin. Yeah.
Did you test on skin?
Yeah, we test. Yeah.
So how did you test on skin? I mean, without, it's just water bottle, right? We want to test the environment for experiment 1. There's no person here.
Yeah, no, we don't have the figure shown in here.
Did you test it on skin directly in another experiment?
Yeah, yes, but I don't show the experiment because
Did that work? Did you get a signal?
no, yeah, no close, just the
Okay.
direct.
This is what I'd expect. If you put it right on a conductor, you're not going to get a signal back. If you put the RFID tag right on a conductor, you don't get much of a signal back. As you pull it away from the conductor, you'll start getting a signal. And that's why last week we were talking about getting a piece of foam or something that's a known thickness, and then you can measure the signal as you bring it away from the conducting plane. Right? You put 1 layer of foam, 2 layer of foam, 3 layers of foam, and pull it out and see where it has to be. The trouble with cloth is you have no idea how far it is from the conducting plane.
Okay.
It's a completely uncontrolled experiment. I can
Right.
see the wrinkles in the cloth and so on.
Right.
Yeah,
But-
you can get a
but-
nice piece of foam and just pull it out.
Okay, the Tianmin conduct the experiment.
The strange thing
yeah.
is that in this experiment, with the water tank or water bottle, they also don't have the signal. And supposing the bottle is plastic, it's
Right, but how thick is the plastic? That you have, that's
Not
a
a
good
conductor.
information. The plastic is about 5 mils thick, maybe a millimeter thick. Okay, so it says that a millimeter is too close to a conducting plane. So now you have to do some experiments, say 3 millimeters, 5, 10. How many millimeters do I have to be away from a conducting plane before I can see a signal?
I see.
Okay. So you have a good and the thickness of your skin, there's maybe maybe a 1/4 of a millimeter on top of your skin that's not really conducting, that's dry and has different RF properties. And so a millimeter is too close. And how far away do you have to be? Well, you do the experiment. It only takes you a minute to make the measurement. So you put a couple layers of foam on there and bring the tag out until you start seeing a measurement. The same thing when you have 2 tags like in figure 4 side by side. What you do is you start with 2 tags like this and you bring them closer until it starts acting funny. And then you know how far they have to be, because otherwise you're just pulling a number out of the air that has no meaning behind it. I mean, it's about a wavelength, but you actually have to do the experiment. That's only a couple of minutes, right? To make that a scientific background. Then you have knowledge, you can plan your future experiments.
Yeah.
Okay.
Yeah. So your suggestion is that ask him to use the foam, put the foam in between the skin and the tag.
Right. Something that's not conducting, that's mostly air, that would be fine.
Yeah, actually, on my site, I tested the foam.
Oh,
And,
really? Okay.
Yeah.
Yes, the foam is 1.5 millimeter. And when I attach that on the water bottle, I can receive signal. Pretty good.
Good. Then you can do 2 or 3 layers of foam and make a plot.
Yeah,
And
I
the
will
plot
try
will
that.
go, the plot will go like nothing here, and then it gets better and better, and then it's okay. And you want to know what
I
that
see.
curve is, right? The curve is no result here for 0 thickness or maybe a millimeter. And it gets better as you get further away, and then it flattens out after you're, I don't know, a centimeter, 2, 5, something like that. But you have to find out what that number is. I can't pull it out of the air.
I see. Okay, I will try that.
Same for the skin, same for the person. That's why I'm worried about somebody that's either anorexic or obese, because it will affect the signal dramatically unless you have a way of controlling for that.
Okay. Okay.
That would be, yeah, if we can see some kind of plot, I think that would be great. To just to actually enhance our knowledge.
Okay. So also we observe that even though the environment is it keeps silent and static, so we can see the noise, yes, up and down, right? Yes. So in the first, in the second and three figure shows.
Yeah, and also being, I need to remind you every time you need to keep the y-axis, the readings consistent. I mean,
Okay.
when you plot, yeah, if
Okay.
it's you use the different scales, we cannot
Mm.
compare, especially later on when you have readings, right? Right
Yes,
now,
yes.
this is the ambient environment, right? And when you have the breathing, you want to test the breathing, right? It's you need to put all in the same scale so that we can do the comparison.
Okay. Okay, so next slide 10 shows a summary for experiment 2. So this experiment, I attached one tag horizontally on the good position. Yeah, in here shows in the figure, and also use the three different distance between the antenna and the subject. So the above.
Yeah, so again, okay, if you compare with your previous plot, right? These two plots are not, you cannot compare them at all. You look at it, right? For your y-axis.
Different.
Wait, can you go back to your previous slide? Yeah, you have 6 and 4.5, 6.5. And the next plot, next slide, you have 1.4, 1.8, 6, 1.
And different zeros
huge
and
difference.
different zero positions. The zero axis is someplace
else. The zero axis
Yeah,
is shifted also.
I should use the same.
You might end up having to have the vertical, the delta y be the same for each one, because I imagine the 0 point is going to move around as somebody breathes or the room temperature changes or the door opens or something. You can have you can reset the 0 for the plot, but you want to have the delta to be the same.
Okay, so I can okay.
Yeah, you need to mind that, otherwise you cannot compare your results, right? When you told us the signal is fluctuating in the ambient environment, and how fluctuating they are comparing to when you testing with your breathing, right? You need to put that into perspective.
Okay.
Yeah, when you plot these figures, I think you should compare these figures with the empty room.
Yeah, you yourself, you need to ask yourself questions, right? You cannot just say the ambient environment, you say, oh, it's fluctuating. The environment is not stable. But how stable it is comparing to when you have the human readings in it, right? That is the part we need to compare, because the signals, RFID, their wireless signals, they're going to be fluctuating like all of our other experiments, other projects, right? But you need to put this into perspective.
Okay.
You need to ask yourself, right?
Yes.
If you sit very still, not in the direct beam, and the door is closed and nobody else is moving around, how stable is it actually? Okay. My experience is that it's pretty good if nobody's moving.
Yeah, it should be.
So you should have that as a baseline to understand what's going on, and then do the open and close the door, have people move around, and see whether you can get enough changes to give you a false reading.
Okay, so to explore more experiment and so here is the
not more experiment. I think you have to do some very controlled experiment.
Yeah, very controlled.
Probably just do 1 or 2. Yeah, and then see that what is the signal look like.
Okay. Okay, so the SS10 shows that in the different distance and with the normal breath and the deep breath, we can get the clear breath pattern. Yeah, so in the good place. So it's the experiment 2. Next slide is experiment 3. So in this experiment, I just attached the vertical tag in the 9 different place. And
so one question for the previous slide for experimental 2, you just showed to us. Yeah. So for this 6, basically those are the same tag position, right? The same tag position, and you're moving to the different distances.
yes,
Okay.
same tag position.
And you know, I would argue that an equally useful measurement is to have the distance constant and move the tag around on the chest and plot that. A heat map, basically, of the signal strength on the chest at a fixed position, and everything else is stationary, and get a heat map of that. And then you're going to put 3 tags on eventually, so or at least put 2 tag on. Take a map of the tags as you move them closer and further apart. The heat maps are really powerful presentation tools and understanding comprehension tools.
Okay.
Yeah, I agree.
Okay.
Yeah, so probably you keep this 1 meter distance, right? 100 centimeter, 1 meter distance, and then try to plot the heat map for
Okay,
experiment.
1 meter.
Yeah, I think you can write down for each experiment what the suggestions we give to you.
Yeah. And okay, so the next slide is yes, vertical. Yeah, I put the vertical tag on different positions on the chest and the boundary of the chest and abdomen. And
Excuse me, which way is the reader polarized?
sorry.
What's the polarization of the antenna on the reader? Is the reader up and down or back and forth?
A reader is upright, particular to the ground and towards to the subject.
Right, but is the antenna on the reader going up and down
Antenna,
or this way? Yeah.
Antenna, sorry, antenna.
Antenna, is it
Antenna.
up, down, or horizontal?
Yeah, vertical up down, should up down. Yes,
Okay,
here
good.
we can see that it's up down.
I
Antenna
can't
the left.
because that's a square antenna.
Ah,
What is the you know what
I think-
polarization is? You know what
I think
polarization?
Rich is saying that this antenna has its polarization. So where
Yes,
polarization.
it has directions up and down, and since it's square, and it's not sure that in the picture how you put this polarization direction.
right. You have to look it up. It might even be
Yeah.
circularly polarized, but if you care which way the tags are oriented on the person, you have to know something about what the reader is doing. So you should look up the data sheet for the polarization of the antenna. And then you should try your antennas. You have an antenna like this. You should try it like this. You should try it like this. Again, make a map as you rotate the antenna around, what difference it makes. If it doesn't make much difference, that means your signal is all scattering in the environment. If it makes a big difference, that means you're matching up to the antenna. So you
Right.
should have a plot of that.
okay. So
Excuse me.
So keep the tag, keep the distance, keep the tag orientation. Don't change the
and-
tag. And then you change the direction of the antenna, the readers.
At the same position, right, exactly.
okay.
Right. These are essentially, you have a high dimensional space that you're trying to map out to do this project. And you have to take little cuts through this dimensional space and see how these things, what's sensitive and what's not. It's like principal component analysis. What are the things that matter and what are the things that don't?
Okay.
And you can only determine that by making careful measurements, ground truth measurements.
Okay. Okay. So here is
So
the.
Bing, I think you need to speed up. Yeah, it's already about half an hour. So also besides, I also want to remind all of you guys that you find 2.
Yeah,
papers
I
that
also
are
want to
very
discuss
similar
about
to
that.
the
Yeah.
paper. So let's quickly go through these
Okay.
experimental results, and we need
Yeah.
to.
I think
look
we
at
need to
those
go
2
through
papers.
those 2 papers. Yeah. Actually, I told Bing right before the meeting.
Okay.
Yeah, ask him to quickly go over his results.
Yeah.
Okay. So the okay, page 12 shows the result for this experiment 3. So we can see that for the horizontal and for the vertical tag in the good place, we can get the clear pattern for each scenario, even with the breath and the deep breath. And for the experiment 4, I attach the tag on the good position in different directions, 1 and 2. 1 is 45 degree and 2 is 135 degree. And also we can get the clear pattern with the deep and normal breath in the same distance, 100 centimeters. And yes, so this is the result. And the next
So do we know that the direction matters? Which direction you have the best signals? Since you're trying to test that, right? Then
yeah.
Simply clear is not good enough. Since you put it in a good position, it's supposed to be clear. But which direction is better? Does it matter or it doesn't matter?
Okay. Yeah, okay, I should put it in the same scale to compare them. Which one is the...
Yeah, currently I think the scale is the major problem.
Different.
We didn't put them into the same scale, so it's hard to compare. And also I would suggest you, okay, because the red curves are the ground truth, right? Your blue is the is what you measure. I think you should, let's reverse it, okay? Use the red for what you observe, and then the blue is the ground truth. And also when you plot the red, okay, the tag readings, use a thickened line. Okay, you can change the thickness of your line so that, because that is the something we like to look at, right? So currently, I think your red actually is dominating. I can barely see the blue.
Yeah, you need to.
You can replace the solid line.
Understand what we want to see and what is just for the comparison.
Okay.
You can make the red not only make it a different color, but you can make it a dotted line. It doesn't have to be solid.
Right, right. Yeah.
Okay.
So it's just faint. So it's a background that helps you guide your eye.
Right. Yeah, exactly. Yeah.
Okay, I see. And I will improve this. And also, so this slide 14 shows the comparison between the different direction. The last experiment I want to report is that.
So you need, as Ian suggests, you need to draw conclusions from those, right? You need you need to ask yourself, when you put this together, you need to ask yourself, what did you observe from this, right? Whether it makes sense or not. And when you show it to us, can we see them clearly or not?
Okay. Experiment 5, we use 6 scenarios, use the tag arrays. Some is attached horizontally side by side, and some is vertically. Last one is one tag is particular to the tag 2, and we found that in my experiment, the scenario 4 and scenario 6 can get the clear breath patterns for both normal and deep breath. For the arrangement 5, I can only get the clear pattern with the deep breath, and for other we can get the noisy readings. And also in the slide 18, I shows the best scenarios, arrangement 6 and arrangement 4. We can get the clear breathing patterns for 2 tags. Yes. So this is a experiment. So also in the previous slides, I think in the 51, like the Professor Richard Howard said, that I also here, yes, I put the different positions horizontally in this area. That also I need to make up the heat map to show how the tag is sensitive to the different locations.
Oh,
so this,
nice.
Did you do it?
Do you have a plot?
No, I didn't know. I will make the heat maps. Yes, according to your suggestions.
That's a great way to do it. Yeah.
Yeah.
Okay. And so for summary, I want to summarize my experiment. Okay, see here. So we found that we found the good positions that in the first figure in the yellow area. So in this area, we can get the clear pattern, breathing pattern. Yes, in different directions, tag directions, vertically or horizontally. And also that Tianming double validated that this good position. They use the tags attached on the skin by using the form. And the second one, we observed that the different environments impact the distance range. For my experiment, I use the 3 distance between the subject and the antenna. I can get a clear breath rate, but for the Tianming in here office room, he observed that longer distance usually leads to the worse readings. Yes, and the third observation.
So for this part, I think when both of you analyze these results, you need to have a criterion to determine what is a good result, right? What is a clear pattern? And to me, I think when you analyze your results, it seems a bit vague. When you say in a certain position, it has a good pattern or a clear pattern. It seems other positions also have some pattern, but how do you determine it's a clear pattern?
Clear and a good pattern, yeah.
I think you need to have some criteria and definition here.
The classical criteria. Oh, go ahead. Sorry.
Yeah. Rich, you can start. Yeah.
I was going to say, this is a communication problem. You have a signal that's at the chest, and you're trying to communicate it to the transmitter. And there's enormous amount of work on this. You want a signal to noise ratio, and that will tell you what your error rate in the channel is going to be. And you can just look at it as a communication channel and use all of that machinery that's in place to tell you how good the connection is. Oh, I'm sorry, go ahead, Ying.
Okay, yeah, I think Bing, you need to start derive some matrix, okay? Matrix, okay, to or at least features you want to look at, as we talked about, like amplitude, variance, or you use sliding window, okay, to look into that. Those are the starting point, because currently you only use your eyes, right, to do the comparison. But okay, when you say, okay, how you measure, okay, distance, how it will, the distance will affect the readings, and whether the orientation of the text will affect your readings. All of this, I think you need to use, matrix. If it's not complex ones, but you need to start with simple ones.
Okay.
Yeah, to look into those data.
Okay. Okay, so okay, the third observation is that we found that the RFID signals are sensitive to the different humans. For my experiments, for example,
and also how sensitive they are, right? Those also you need to quantify, because we know that all the wireless signals, they're sensitive to the environment and they're sensitive to different person, right? So how sensitive they are, okay, whether, okay, like in this case, shall we differentiate person, okay, using this, okay, or not? Okay, this is also some directions for the project. Okay, if we want just to do the well-being monitoring, okay, whether we want to do it just per person, okay, then we also adding the personalized well-being monitoring into this, right? So if it's sensitive to the person, sometimes it is a good thing for us.
Okay.
Right? Yeah, just like, in our using wireless signals, using Wi-Fi to do user authentication, it is actually for different person, we see, difference. So it's, in order to capture the difference, you can use applied deep learning methods, okay, to see to perform user authentication. So those are the possible directions we can go. We, on top of this breathing measurement, once we get the breathing measurement, we'll be able to see that if we can differentiate person, that can actually lead us to a more in-depth study.
Yeah.
Okay.
I agree. I think actually that's a very interesting problem. I think if you, let's say if you have multiple RFID on the skin or on the cloth, clothes, then you can combine all the information to see whether it's from a different person. Right? I think that's a very interesting question.
Yeah.
But
possibly,
here,
but the clothing, the cloth is not a controlled. If you want to be able to tell the difference between people, you have to have some things held constant or known.
Right.
And the cloth is absolutely not reproducible.
Okay, so in the
Right.
controlled environment.
So as you saw, a millimeter, you don't get any signal. A few millimeters, you start getting a signal. So at the distance over which the cloth goes between the RFID tag and your skin, that distance is a very strong function. I mean, the signal is a very strong function of distance.
Mhm.
And any signal that's different because of the shape of the person is going to be smaller than that.
Mhm.
Right.
So you're going to be dominated by the irreproducibility of the cloth.
I see.
If you don't have the tag on the person's skin. I mean, you'd like to have it woven into clothing. I understand that. But that's a hard thing to do from a radio point of view because it's on top of a conducting person.
Mhm.
Mhm. Okay.
And
Unless
and
you separate the tag, push the tag away from the body a ways.
yeah, I think that's hard to determine.
That's hard to determine.
Yeah, that's hard. Yeah. So
So in this
yeah.
in this one, I want to point out probably we cannot draw the conclusion that it's from different people because since you and Timmy are conducting the experiments in two different environments, the setup and
yeah.
the entire setup could be totally different. A little bit, at least the difference should be significant enough to affect the results, right? So it will be better to have two people in the same environment to test whether it's sensitive to different people or not.
If you
Okay,
put
I
two
will-
people in the same environment, the wavelength is about 30 centimeters. People are bigger than 30 centimeters. So you can't have two people in the same place so you can make the comparison.
Mhm.
They have to be in different places relative to the multipath signal
Okay.
because they can't be inside of each other. So it's going to be very sensitive to that, but not reproducibly.
Okay. And next
Yeah,
observation that
and actually, just to add, I think you can read a couple of other papers that I'll send to you later on. One is the previously we're using a Wi-Fi signals to monitor breathing rate to do user authentication. I think Tianming is also involved in that work. And also we have the previous work is to utilize just Wi-Fi signals to authenticate people based on their daily activities. So you can read those two papers and then see if later on we're going to use the RFID tags to also differentiate people, okay, what we could do. So I think you need to start reading those papers also.
sure, Professor.
Yeah, I also send those papers to the whole group so that Tianming and Hao can also take a look.
Sure.
Okay, so yeah, so let's continue. I think probably we should read the two, go over the two papers
Over
that
those
you
two
guys found.
papers, yeah.
Okay. So okay. So the slide 20 is the first papers I reviewed. The title is Tag Breathe, Monitor Breathing with Cognitive RFID
I think probably we should look
systems.
at the one that's I think Tianming, or you mentioned, I think Tianming mentioned that he found a paper that people also put RFID tags on the clothes to do certain kind of monitoring.
Yeah, that's one of them, Professor.
Yeah.
Is this the one also?
Yeah,
Yes, this is the
one
one
of the
Okay.
two papers.
They found
Okay.
two. Yeah, they found two.
Okay, I see.
Yeah.
Okay.
In this paper, the authors proposed a system that can monitor the breathing rate with multiple users. So here is the approach. First, they use the face calibration because they use the same reader with us and have the frequency hopping.
So where where are the tags being placed?
They claimed that they attached the tags on the chest, but we don't know the exactly location. They attached the 3 tags.
So each person has one tag.
3 tags.
Each person has 3 tags.
We don't know
So what's
the arrangement.
the placement? They didn't say the placement.
Yeah, they didn't say.
That's very strange.
Yeah, but they didn't say how to attach these 3 tags on the chest, which location, what's the
So
arrangement.
there are no figures in the paper.
No figures. Yeah, no figures.
Okay. So where is this group coming from? This is
TMC.
published in TMC, right? Transactions for Mobile
Yeah,
Computing.
TMC.
So where are this group coming from?
Okay,
You need to mind, okay, every time you need to mind where this research group coming from, okay? Especially when they're doing very close research with us.
Okay. Okay, I will search
You need
it.
to have that habit, okay?
Okay. I thought I forgot.
Usually it's not just a paper. You need to see the, the authors, and then to see that if they have a series of papers or working in this area.
Okay.
Yeah, I think I told you many times, right?
Okay. Yes.
So I think the professor, the faculty in this paper is Yuan Qingzhen, which is from Hong Kong Polytech.
Hong Kong Poly.
The Polytech University.
Okay, this set also shows the approach how they extract the breathing rates. First, they conduct the phase calibration. Second one, they calculate the displacement of the tag. During the 2 consecutive phase readings, they use the phase to calculate the displacement. And then they normalize these displacement values, shown in the figure 6. And in the next slides, they apply the FFT to convert the time domain displacement to the frequency domain. And also they use the low pass filter as 0.67 Hertz because they know the average breath rate for the people.
Oh, I also have another question. Okay, Bing, I think here you also need to pay attention. Tell us in the paper, you said when multiple people around, right? Do they monitor every person or just monitor one person when you have multiple people around?
They have the multiple people. They multiply
They monitor everybody.
Yeah, everybody.
Okay, then how do they separate these tags?
Yes, because each tag has the unique ID. The EPC
so they use the ID to separate.
Yeah.
Okay,
yes.
So they know that, for example, 1, 2, 3 belongs to you, and then the 4, 5, 6 belong to Tianming.
Yes.
Okay.
Yeah.
Exactly. Yeah. Yes. Also, they can code this ID for in each group.
Okay.
Yes. Also, after they convert the FFT to domain, then they use the inverse FFT convert back to the time domain, and then we can show in the figure 8. So for this paper, they don't calculate peak. They just calculate the 0 crossing point to calculate the average breath rate. So this is their approach. And also for the data fusion, because they have the multiple tags on each person, so they aggregate the displacement value for n tags for time interval, for example, t and t plus theta t. And then for the n times intervals, they measure the total displacement.
I think we should focus more on the scenarios that similar to our ideas. The details probably we can go.
No, we can do a secondary
later.
Yeah.
Okay.
But we want to see that whether these papers are really close to what our idea were. Right.
Okay.
Yeah.
And the next slide shows the experiment setup. So they use the same reader with us. I use the different tags.
I think Ian just talked to you that we need to focus more on the scenarios. So what kind of scenarios they position their work?
Scenarios they use here 24.
What the motivations, right?
Motivations, they want to monitor the breath rate for multiple users. So this is the main idea.
What kind of scenarios?
Scenarios is that in here, just office room and 1, 2, 3 users and side by side in the second bullet. Yes, 4 meters away from the antenna, and each person attached 3 tags on the chest. So this is a scenario.
They also put the tag on the clothes using the backscatter signal to monitor the breath. This is very similar to our work. And in their experiment, they also test the different distance from the antenna to the people, and also test different postures like sitting, standing, and laying down. and also test different number of users.
Yes.
So their case is that they put it in the medical scenario or just a regular day. So the people mostly are static, right? They're sitting in office or things like that. Is that
daily life scenario?
Daily life scenario, and then mostly the person's just static, right?
Static daily life scenario.
Okay. Yeah, because we need to justify our approach, right? Bing and Tianming, right? So if they have those paper there and just published recently, 2019, right? How do we justify our application?
Okay. So this is the first paper.
So what do you think? I'm asking you, not okay. Okay. Oh. This is not okay.
I think
you need to, once you see this paper, actually, both Ye and I, we got very worried, right? The other day, we told you that, okay, we thought of this is a good idea, that we haven't seen people put RFID attached to their clothes to do the monitoring, breathing monitoring. And now we see a couple of papers working in this area, right? And they've already did some pretty advanced work because they're working on multiple people together at the same time. So we need to think about, actually, you don't need to give us so much details of this paper. You need to actually put in our applications side by side with theirs, and what we can do right now side by side. You need to do the side by side comparison.
Okay.
What's the difference? What's the novelty of our work to theirs? So that is the question. Okay, when you read such papers, you need to get worried and then think deeply. Okay, what's the difference between our work and their work? What's new we're doing that they haven't done? Then you'll be able to publish. Otherwise, you won't be able to publish.
So, Professor, I think they didn't compare between different users in terms of this breathing pattern. So probably we can try to using breathing rate. Yes, to like authenticate user.
Yeah.
And yes, or even come up with
identify user, yeah, or
identify
just user identification, like in the emergency situation. One possibility is in the emergency, as Rich talked about, okay, have the charge situation. We can identify which person's breathing rate is that, so that we can, have that person got the medical treatment sooner, or in some other cases, we can think about, okay, when you use, again, like sitting from the computer or access the smart appliances in the smart home environment, you will use that to identify, okay, only the adults in this household can operating, for example, hot stoves, while the elderly people or little kids, they're not safe to operate the smart appliances. So we can put those in that scenarios. So those are the two scenarios I can think of. So I hope Bing and Tianming, you can write it down, put them into the.
But one question is, since the RFID tag already has and can send a different tag ID.
Tag ID,
right?
Yeah.
So will that be easier to
just use the tag ID.
Tag ID to differentiate the user? I think we need to put some scenarios, maybe the tag maybe shared between people, or I don't know. Otherwise, it will be easier just to use the ID. If
why would you not use the ID? That's what it was designed for.
Sorry?
Why would you not use the ID?
Oh, yeah.
That's what it was designed for. There's an international consortium that defines the data types and how the packets move them around, and the hardware is all set up for it and everything.
Yeah, it's originally designed to differentiate the objects that the ID attached to, right?
I mean, the tags were designed for inventory management, very specifically. So they have 96 bits of MAC address for that purpose.
I think
so because we are looking at, because if somebody else is already doing this, measuring the breathing rate, right? So we like to see that what are the unique problem we can look at.
Mm.
But as just Ian pointed out, that if we want to look into the user authentication problem, but the tag ID is already there, right? So we can use the tag ID to easily identify different people.
Yeah.
Yeah.
User
Professor,
identification would be interesting if you had a passive system without a tag on the person. So you would use the reflection back from the different parts of the body. You could imagine doing some kind of authentication thing that way, but they'd have to be facing the right way, and the clothing would have to be right, and no metal belt buckles, and it's a hard way to authenticate people.
Sorry, did you say the ASIC system?
These are, I was saying, if you had a passive
Passive
system,
system.
which means no
Without the
tag on the
yeah,
person.
That is just like
Right.
we use Wi-Fi
Right,
signal,
right,
right?
right, right.
I mean,
Passive,
from my-
just device
passive.
free, basically.
Yeah, yeah.
Yeah, from my point of view, if you're going to put something on the person,
So you'll be
there's
able
no
to
real
identify.
but there's no real advantage to using a specific RFID tag, because it's designed for inventory. You're going to put it on, but you're already putting something on the person. It seems to me there are many more use cases where if you don't put something on the person, they can walk by and you collect the information. That would seem to have a much greater use case, because that's screening, not individual monitoring. If I'm going to monitor somebody in a hospital setting, I might as well buy $100 monitor, strap it on them, and monitor them. I mean, that's sort of a solved problem, and the cost is way less than anything else you've got in the medical profession already. Whereas if you have a deviceless way of doing it, then that's a whole different issue. Or if you want to do monitoring of a person while they're in daily activities, there's a real use for that in the medical profession. Then you need something that's not on the clothes, but can be sort of attached to them on a wrist or something that they could wear all day for a couple of days and track their breathing and heart rate. That would also be useful. Those are expensive and awkward now.
Yeah.
Okay, so for
Yeah.
Professor Wang
Can we talk
mentioned-
about the next paper?
Oh, sure. I just have
Quickly, let's go through that, yeah.
yes, one comment that the tag ID is easily to be modified. If you have the reader, you can modify this tag ID. Yes, so that the attacker also can modify it.
Yeah, let's keep that in mind then.
Yeah, we keep that in mind. If the tag could be tag ID could be changed, right?
Yeah.
So we can probably still utilizing certain metric, biometrics like breathing ID and breathing rate to re-identify that person.
Yeah, or it's in a shared system, for example, a gaming system that maybe you can put RFID tag on some gloves or some rings that you attach to it, that whoever that wear that glove
Have
or
that,
ring
yeah,
can identify the person who wear it. That's just my.
Yeah, I think that's also could be a scenario we can think of.
Yeah.
Like in the shared environment.
Another scenario probably is you use the signal to monitor people's health condition, right? So if it's people have been sick, has a difficulty in breathing, so this can compare to his normal breathing patterns.
Yeah, that is more in line with the well-being monitoring side. Yeah.
Okay, Bing,
Okay.
let's quick go through it.
Okay, so for this paper, this paper uses another approach, use the graphene oxide sensor to classify the different breath patterns. Yeah, this is the idea. Okay, they design and implement this prototype, use the sensor, and also they attached on the humans, you can see on the human face and cheek to classify different deep pattern, normal, deep, apnea, different pattern. So because they found that the sensor can have the different characteristics.
So what kind of sensor is this? This still
RFID
this sensor
should RFID combined with the graphene oxide.
So humidity
Humidity,
sensor. So they attach this sensor on the RFID tag. So they changed the RFID tag. So they they put the sensor. Attach the sensor on the RFID
This
tag.
is essentially what I was talking about
Yeah.
Right. I think
the
it's
other day.
like
But what they're doing, this is a really, there's an important distinction here. They're measuring something that has to do directly with breathing, which means they're measuring the humidity of the air that's coming in and out of your mouth. You can also measure the temperature of the air that's coming out of your mouth. That's just a question of what the sensor's like. A thermistor is 10 cents. It's standard technology. You can buy it anywhere and you can hook it up to an RFID transmitter because the tag is just being used as a communication link here. Graphene sensor is a one of, it's a little flaky, you can't buy them. You can't put them into commercial use, and they're demonstrating what their graphene sensor will do, but they're not making a particularly interesting, compact, useful, scalable breathing sensor. If you're willing to put something on somebody's cheek, you can just measure the temperature of the air going in and out of your mouth, and it works just great. It doesn't require much technology, and it's really cheap. And like the thing that the people use in theater where they have a little something taped, or a mask. If you're wearing a breathing mask, that does the same thing. You catch the air coming in and out. But there you're measuring directly what you want to measure, airflow or humidity, right? And the humidity sensors are not usually very good. Regular humidity sensors have a long time constant and they're hysteretic. Graphene may be better, but it's very sexy. It's one of the sexier things that people are working on in the material science world. So that makes a good paper by itself, but it doesn't really solve your problem. You're interested in systems that actually work and that you can build, right, Ying?
Right.
Okay, so this is interesting, but you can make something a whole lot simpler
Okay.
that
So
you could actually make 1,000 of if you wanted to.
Yeah.
There's
I
one of
think
these on the
the other
planet.
day, Rich's idea of have this you have this thermistor sensor, right? Probably we have it integrated with RFID. I think that could also be a good direction to go to.
Yes.
I'm sorry, I have
Okay,
to
yeah, I think Ian needs to go to teach. So yeah, I think probably we stop here today. I think they can do some more experiments, but meanwhile, I think we need to think very deeply, have some brainstorm next time. I think the students, you can list out, in the high level, okay, what we are doing, the setup of our project, what we are doing, comparing to the two existing work that those are closely related with our work. What are their applications? What are their approaches comparing to ours?
I think one of your important suggestions, Ying, was that you need scenarios for how you use these that are not already filled by perfectly adequate sensors.
Right. Yeah, you're right.
Because you're not in the sensor business.
Right.
You're in the systems business.
We're in the systems business, right?
Right. So that means that if there's already a sensor that solves the medical problem and the cost doesn't make much difference to the overall cost of the treatment or monitoring, there's not much of an opportunity there.
Yeah, it's hard. Yeah, that's not.
If you wanted to do triage on 1,000
that's
people, or you had some other, you want to do daily life monitoring, areas where there are not good solutions already, then that's a different story.
Yeah, right.
So you need to identify,
where
there's a hole.
Right, exactly.
And triage is the one I knew about because I was part of that committee on disaster management, but there may be others, and those are worth understanding so you know what the boundary conditions on your technology have to be.
Right. Yeah, exactly. Yeah, so we need to actually brainstorm some more, okay? And then think, yeah, we need to all think about this during this time period. Okay.
Sure, Professor. Yeah.
Okay. Yeah, I think Tianming and Bing, it's worthwhile for you to do some more more the survey, okay, to see that if there are any other work that's related to put the RFID tags on the clothes to do the well-being monitoring.
Sure. Yeah.
Okay. Yeah. Okay. So yeah, thanks again, and we'll talk to you next time. Okay.
Okay.
Thank you.
Okay,
Okay.
Professor.
Bye-bye.
Thank you.
See you
Thank
back
you.
next
Thank you.
year.
Yeah.
Okay.
Yeah. See
Thank
you.
you.
Yeah.
See you.
就咱俩。
来，咱大概说一下我们要干啥来着？下一个阶段。